Alright, in our second video here, we're going to start off with example 3. This is going to go much quicker as far as this specific example is concerned, because we're only doing Green's theorem. We're not going to prove this doing it both ways. So let's go ahead and take a look at it. First of all, we are going to evaluate the line integral. Now it does say to evaluate the line integral, but it says given that it's positively oriented curve. So they're telling us that even though they didn't put the symbol on there. So we've got the line integral of y cubed dx minus x cubed dy, and c this time is the circle x squared plus y squared equals 4. So this is going to be, that wasn't very good, but whatever, we'll deal with it. We've got our circle, and the circle looks like it has a radius of 2. And because we're going to use Green's theorem, and it does tell us that this thing is oriented positively, which means counterclockwise. So we're still going to need dq dx, and we're going to need dp dy. So dq dx, again, remember q is the second component, so that's going to be 3x squared. I'm sorry, negative 3x squared. And dp dy, which is the first component, is going to be 3y squared. And Green's theorem says, take the double integral over d of dq dx minus dp dy dA. So we're going to need dq dx minus dp dy. That's going to be negative 3x squared. Put that up here. Negative 3x squared minus dp dy, which is 3y squared. Well, considering this thing is a circle, and we can factor the negative 3 out of that, x squared plus y squared in terms of polar is just r squared. So I think doing this in polar is going to be way easier to do. So we're going to change this into a polar region. And then we'll have an integral. Now remember, polar is r's and thetas. So theta is it's a full circle, so it's going to go 0 to 2 pi. R is going to vary from 0 to 2. And then we're going to have negative 3r squared. Now we did change it into polar, so don't forget the extra r, dr, d theta. And again, this should be very quick. So we can actually split these. We can have our integral from 0 to 2 pi of d theta times our integral from 0 to 2 of negative 3r cubed dr. So let's go ahead and take the antiderivatives here. Well, we know 0 to 2 pi of d theta is going to end up being 2 pi. And then we're going to have negative 3/4 r to the 4th from 0 to 2. So we'll get 2 pi times, let's see, if I plug 2 in there, we're going to get 16. So negative 3/4 times 16 is going to be 16 divided by 4 is 4, so negative 12. And then plugging 0 and we get nothing. So this thing is going to give us negative 24 pi using Green's theorem. Again, much, much easier to do than the standard line integral. Alright, we are going to get into the proof of Green's theorem, because if nothing else, you should have at least asked yourself, okay, this is great that this works, but why does it work? So here we go. And if you're not much into the proofs, then you really don't need to watch the rest of this particular part of the video. If you like the proofs, here we go. So I guess the question is, what exactly are we trying to prove? Well, this is what we're going to prove. We're going to prove that the line integral over c of p dx plus q dy is the double integral over d of dq dx minus dp dy dA. So what we're going to do in our particular problem, because I'm not going to do the whole thing, it's very tedious and very long, we'll prove that the line integral over C of the pdx part, so just the first part of our integral on the top there, is going to be the negative double integral over d of dp dy dA. Because basically if we prove this part equals this part right here, then the proof for the q dy and the dq dx part is going to be pretty much exactly the same thing. So we don't really have to do it twice. There's going to be an aside over here. It's kind of a, oops, again I'm trying to draw with an eraser. It doesn't work so well. There is an aside, and the aside says that if I have some kind of a curve which goes from a point to a point, we're going to call that, oops, not C1, just C. But if I have a curve which is exactly the same curve, we're going to say it's the same, even though I didn't draw it exactly the same. It's close. And it goes this way. Well, then isn't that just going the opposite direction? So we're going to call that negative C, since it's going backwards. Same idea. So again, we're going to prove the one that I wrote in green over there on the left. You can, if you choose, that the line integral of q dy is the double integral over d of dq dx dA. You can prove that one on your own at some point if you find that you have that desire. Alright, so let's see if we can do this proof. Not the easiest to follow, so I'll do my best to try and help you guys along here. So what we're going to have is we're going to have some kind of a figure which is going to be bounded by a and b on the x-axis, and our first curve is going to do something like this. It's just going to be some kind of wavy curve or whatever. It's nothing specific. Our second curve up here doesn't have to mirror it, might do something a little bit different, something like that. Who knows exactly what it is. We're going to call that one, we're actually going to call that one C3. But we're going to label these. This one right here, we're going to call some kind of a function of x. So we're going to call it g1 of x. And then this one up here, we're going to call g2 of x. Two different functions of x there. And because they are bounded by a and b, we're just going to draw vertical lines here around a and b. So we're actually going to call this part right here C2 because it's part of the enclosure there. Because remember, this has to be a closed, positively oriented figure. So in order to positively orient this thing, it's got to be going in this direction all the way around, something like that. Okay, so we're going to do this in two parts. What we're going to show, first of all, we're going to show what the double integral over d of dp dy dA is equal to. And then once we show what this is equal to, we're going to show, let's just go back up and remind ourselves, we're going to show what the actual line integral of over C of p dx is. I'm sorry, yeah, p dx. So we're going to show both of those things, and basically what we're going to do is we're going to show that they're equivalent to each other. So let's develop this double integral over d of dp dy dA. So the double integral over d of dp dy dA is going to be a double integral. Well, the integral, if we do this as a type 1 region, the x values go from a to b, and the y values go from the bottom where the c1 and c3 are, from the bottom c1 to the c3. So they're really going from g1 of x to g2 of x, two functions of y there. dp dy, and since we did it as type 1, dy dx. Okay, these things can actually be split. What I'm going to have here is the integral from a to b of, now if I take the, I'm sorry, it's not going to be split, we're just going to do the antiderivative. We're doing the antiderivative first with respect to y. Well, I've got dp dy here, so if I take the antiderivative of that, it's just some function of p, but p could be a function of xy, and we're going to evaluate that from g1 of x to g2 of x dx. Okay, so then by plugging in g2 of x for y and g1 of x for y and subtracting, we end up with the integral from a to b of p of, number, we're plugging these things in for y, so it's p of x comma g2 of x minus p of x comma g1 of x dx. Alright, this was part 1. So what we just showed was that that thing right there is equivalent to this. Now we're going to do part 2. So let's go ahead and separate this. So part 2, we actually have to find the line integral. So the part that we're going to be showing is the line integral over c of p dy. The line integral over c of p, I'm sorry, it's p dx, excuse me, I have to rewrite that, p dx. Sorry about that. There we go. So that's the part we're going to show now. So let's go ahead and do this line integral. Excuse me. So we're going to do, well, C2 is actually pretty easy to do here because it's a vertical line. So let's look at C2. C2 is the vertical line which goes from, let's see, x is going to equal to b all the time. And the y of C2 doesn't really matter because dx is going to be 0. So in that line integral, when we take the line integral for C2, we're going to get p, whatever p is, times 0, so that's 0. If we do C4, very similarly, that's going to be that vertical line where x is equal to a, so dx is then also equal to 0. So then the line integral over C4 of p times 0, and I know that that looks here, let's write it like this so we know it's p times 0, not p of 0. That's also going to equal 0. So now the ones that we really have to concern ourselves with are C1 and C3. So let's take a look at C1. Let's do C1 right here. C1 is the one that has the g sub 1 of x. So C1, we're going to let x simply equal x, and we're going to let y equal g1 of x. So because we don't really need the y part, we're not going to have to concern ourselves with finding the derivative there. But I do need dx. Well, dx is going to just equal dx. I know that this is going to go from a to b because that's what it says up here. This is not a simple line. That's why I made it wavy, so it's not just 0 to 1. So I do know that our bounds for x, a is less than or equal to x, which is less than or equal to b. So my integral becomes the integral from a to b of p, but p is a function of x and y, but we've decided to say that y is g1 of x, and dx is just dx. Okay, let me move my paper down here just a little bit. So now let's look at C3. Well, once again, in C3, we're also going to let x equal x. And we're going to let y equal g2 of x. Once again, dx is dx. And in this case, normally what we would say is that x goes from b to a, because if you look, again, C3 is going from b to a since we're traversing this thing counterclockwise. But we don't want to do it that way. We want to actually get it to go the correct direction. So this is where this little aside up here says that if we have c, which goes in one direction, if we turn it around to go the other direction, it's really negative c. So really this c3 down here is going to become a negative c3 in order for us to get this to go the correct direction. And therefore, x can vary from a to b. But that's for negative c3. I don't like that 3 very much. Let's get rid of that. That's better, C3. So this is the case where negative C3 will go from A to B. X and the Y are still going to be X and G2 of X. No problem there. So the integral that we're going to have now for this one is going to be the integral from A to B of P of x and g2 of x, dx. And don't forget that this is the same thing as the integral of over negative c3, because the a to b is going in the correct direction. So my entire integral over c of p dx is going to be the integral, because I have to add these things up. These two things here are 0. They don't give us anything, but I have to add the c1 and the c3 part up, is going to be the integral from a to b of the first one, p of x, g1 of x, dx, minus the integral from a to b, because I'm really adding this negative of p of x, g2 of x, dx. And the reason that I wanted to do it that way is so that now I can combine these two integrals since the bounds are identical, which will be the integral from a to b of P of x g1 of x minus P of x g2 of x dx. And what you should see is the line integral is exactly the same as the double integral that we just found above. So this is the same as this that we found in part 1. So this was part 2. And they are the same thing. So we've just proven half of it. Again, you could go back and do the other proof for the other half, but I think that that's probably pretty good for right now. So let's move on to actual examples. Alright, these next two examples should go pretty quickly, and then there's one last concept right at the end that we'll talk about. So let's evaluate the line integral of a closed and counterclockwise or positively oriented region. Again, we know that because of the integral symbol with the circle on it, of y squared dx plus 3xy dy, where C is bounded by the semi-annular region D in the upper half plane between the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. Semi-annular region, I've actually never heard that before. Well, it's not true. I had heard of it, but I had never heard of it before doing this specific example. So this is what this is talking about. If we were to take a look at your standard xy plane, it says in the upper half plane between the two circles, so it looks like what we have is a circle on the top half, or a semicircle with a radius of 1. And we have another semicircle, because it's x squared plus y squared equals 4, of a radius of 2. And we know that it is a closed and counterclockwise surface. So it actually goes this direction. But I think what makes it semi-annular is that it includes those pieces down there at the bottom. And then it comes back around this way. And then goes back that way. So if we want to go ahead and calculate this thing, we're going to do the double integral over D, our domain, of dq dx minus dp dy. Oops, that should be a partial. dA. So our region here is going to be best presented in polar, most likely, because they are circular. So we'll have an integral from, it looks like we're only going to go now from 0 to pi. I'm only going halfway around the circle, and our radii are going to go from 1 to 2. So we know we're going to have an r dr d theta. So now we just have to figure out what we're going to need here in terms of polar. So what we really need to figure out first of all is, well, we need dq dx. Well, remember that q is this piece right here. So dq dx is going to be that thing's derivative with respect to x, so that is 3y. And, whoops, and this one right here is p, so we need dp dy with respect to y is going to be 2y. So dq dx minus dp dy, well, that's 3y minus 2y, so that's just y. And then y, in terms of polar, is r sine theta. So this actually should be pretty quick and simple to go ahead and take the antiderivatives of, because we can separate this one. So we're going to have the integral from 0 to pi of sine theta d theta times the integral from 1 to 2 of r squared dr. So antiderivative of sine is going to be negative cosine theta from 0 to pi, and then 1/3 r cubed from 1 to 2. So let's see here, plugging in pi, we're going to get negative cosine of pi. Cosine of pi is -1, so that'll become 1. Minus, plugging in 0, we're going to get 1 for cosine, so that'll be -1. So we get 1 minus -1 there. And over here, we're going to get, plugging in a 2 for r, you're going to get 8/3. And then plugging in a 1, we get 1/3. So it looks like we're going to get 2 times 7/3, or 14/3. So there's that one. Not too difficult. All right. In example 5, let's use Green's theorem to evaluate the line integral of f dot dr. Biggest thing is you have to check the orientation here to make sure that it applies before we use the theorem. So let's take a look at this and see if we can figure it out. So let's see, we've got a function e to the x plus x squared y, and then e to the y minus xy squared. C is the circle oriented clockwise. Well, that's not right, because they're telling us we've got a circle here, radius 5. Oh, that was awful. Let's try that again. Not much better, but we'll deal with it. A circle radius 5, but it says it's oriented clockwise. Not good. But remember that if I want to find the integral of f dot dr, which is over a negative c region, which this one is because it's going the wrong direction, well, that's the same thing as taking the negative integral over c of f dot dr. So really, I just have to remember to put a negative sign out in front, and then we can make the orientation counterclockwise, which will then be correct. So it looks like, let's see, this is also going to be something we're going to do in polar. It's going to be circular. So we're going to have the integral from 0, this one does go all the way around, so 0 to 2 pi, 0 to 5 for our radius. Once again, we're going to have some kind of an r, dr, d theta. So now we just got to figure out what our dp dy and dq dx are. So let's see, dq dx. Oops, wrong D. Let's go back to blue for this. dq dx. So remember that this is q, so the derivative of that, well, that's nice, with respect to q is just going to be minus y squared. And then dp dy, that's this piece right here, with respect to y, that's just going to be x squared. So what we're going to get is, excuse me, so we're going to get dq dx minus dp dy, negative y squared minus x squared, which is really the same thing as the negative of y squared plus x squared, which in polar is the negative of r squared. This is actually going to work out quite nicely. And I forgot over here to put my negative in because we needed that. But this negative from the r squared that we're going to put in there is really going to help out. So the negative is actually going to cancel itself out there. So we're going to get now the integral from 0 to 2 pi, integral from 0 to 5 of r cubed dr d theta. Once again, we can go ahead and separate these things. So we're going to have the integral from 0 to 2 pi of d theta, which we know will be 2 pi, times the integral from 0 to 5 of r cubed dr. So we'll get 2 pi there times 1/4 r to the 4th from 0 to 5, which is going to give us 2 pi times, let's see, 5 to the 4th is 625, so that'll be 625 over 4. 0 gives us nothing. So we are going to get, what is that going to come out to be? 625 pi over 2? 625 pi over 2. And there you go. Alright, so that was the last actual example. I do have one additional concept, which we're going to talk about on this last page, that what if D is not simple? Meaning, what if there's a hole in the middle of it somewhere? Well, let's go ahead and take a look at what that would look like. This will be very quick. So we've got some kind of a region. Maybe it looks something like this. Make sure I close that off, okay? But we do have a hole in the middle. Something maybe like this. Okay? Well, if the region itself is still closed, which it is, and it's oriented counterclockwise, which this is, be no problem if this thing didn't have that hole in the center, because right now it's not simple. Okay, there is a hole in the center. But here's what we can do. What if we were to take and we were to actually separate this thing right there and maybe right there somewhere. It doesn't really matter exactly where. And I was to say, okay, let's look at the bottom half. Actually, no, let's look at the top half first. We'll call this top half D1. Okay, and that's going to be this region right here. See how well I can do this. That's going to be this region which I'm shading in yellow. That's D1. So that's our first domain. Well, we can actually go ahead and take and find, using Green's theorem, we can find this thing's line integral, because I can, let's do it in red. I can go around this piece, just like we did here, counterclockwise, all the way, but then I can start following this dotted line through here, and then I can come across like this. And you might ask yourself, well, wait a minute, that's fine, and yes, that would be the region of that D1 section, but that dotted line is really not part of it. That's not part of our line integral. It's not part of the actual shape. Yes, you're absolutely correct. So where I have the red arrows on top of the blue dotted line, you're right. That's not actually included. We're going to have to figure out a way to get rid of that. But I could, again, I could do exactly what I just did as long as I could put that dotted line in there. Well, we can do exactly the same thing down here for D2. I can take the Green's theorem, because it is counterclockwise, and go this direction. And then, when I get to the blue dotted lines, now I can go backwards. Right here, this is part of the figure, so there's no problem there. But then when I get to this blue dotted line, I can go backwards. So what I am doing by going backwards is I am basically taking out everything that I just put in with that blue dotted line by doing the bottom part of this thing. So it actually means all this is that what we get is we get two simple closed regions. And because of the fact that we negate those blue dotted areas out because we're using them twice, one in one direction, one in the other direction, the ultimate thing here is that Green's theorem still holds. But what you have to do is you have to take out those dotted lines that you've pretty much just inserted so that you could make it two separate closed regions. So it can be done. All right, very long section. I apologize for the length of it, but there you go. Green's theorem, very, very useful theorem.